Okay, here we are, Lecture 3, Pressure Variation with Depth. There's really not a whole lot to say. Anyway, I hope you all having a wonderful, stormy, what's today, Monday? Stormy Monday. All right, I'll try not to laugh too goofy today. Anyway, today we're going to talk about pressure. We're going to define it. We're going to express in different notations. There's like a million different notations for pressure and like so many different units. But the key is, when I say different notations, I mean the difference between gauge and absolute. Gauge is a word I can't spell. I think I actually have it in front of me on Wikipedia so that I'll actually get it right today, or maybe if I remember to look. And then I'm going to define Pascal's law, which is pretty cool. I'll post a video actually to, this guy. I don't really know what his name is. A crazy old man. Who does some really cool stuff on Pascal's. Actually, all this guy's videos, if you're just bored and you want to learn some science, I recommend watching them. He just does a million demos. And then we're going to understand and apply the hydrostatics law. And we're actually going to kind of start on hydrostatics because that's where we are. Like, that's just kind of something to think about. And so hopefully this word jumps at you. Statics, no movement, and static, okay? And then hydro, fluid, okay? So this is fluid at rest. So whenever you see the word hydrostatics, okay, immediately you need to be thinking, okay, this is not a flowing fluid, okay? And you might be thinking, well, but we want to do a fluid. Of course we want to do flowing fluid, but we're just not there yet, okay? So we're going to start with static fluids, hydrostatic fluids. And then in a fluid at rest, there is no shear, okay? So remember, with any kind of fluid, if there's any kind of shear stress, the fluid will flow. Okay, so clearly, a fluid cannot resist a shear stress. It has to deform, or as they say, deform continuously / in layman's terms, flow. Okay, so there are only normal forces. And the key of those normal forces is pressure. Okay, pressure is the key. Okay, so typically, if we want to talk about what is the average pressure, and this is really the kind of the definition for pressure, but the average pressure is usually defined as pressure equals the force divided by the area. Okay, so typically, like if you have some block or something, and there's a force on it, okay, acting, say, to the left in this case, and this block has an area of A, okay. I really don't know how to say that that's the area for, this is the area right here. Obviously the area is not a vector, so it doesn't really have an arrow. Anyway, whatever. Is that, if you take the force, the force and you divide by the area, you get a pressure. Okay. And actually, I'm going to delete that because I don't like to think of pressure. Pressure is not really a vector. I guess it could, I don't know. It depends on how you define it. Anyway, so the pressure at a point, okay? So basically pressure is just kind of a distributed force. It's a force that's distributed over an area. And then if you wanted it at an individual point, okay, P equals the limit as the area goes to 0 of F over A. Okay, so basically it's just an infinitely tiny little, force, okay, on an infinitely tiny little area. Okay, well, it's obviously not an infinitely tiny force. Anyway, so the units in this case, we can work out, okay, and always remember, you can figure out units if you don't know. Okay, so the units look like this. Okay, so we've got a force. So force equals mass times acceleration, so that's mass times acceleration, which is length over time squared. Okay, so that's the force bit. Okay, and we're going to divide that by area, which is length squared. Okay, so there you go. Boom, we've got our units. Now we want to simplify that because that's kind of ugly, right? So we get mass over length times time squared. Okay, so anytime you see mass over length times time squared, you've got a force, although typically what we're going to use more commonly if we have force over area is we're going to use a unit of force over a unit of area. So depending on what system of units you work with, that is either in the SI system, that's a Newton per meter squared, okay, which is the same thing as a Pascal. Or if you're in the dumb units, what do we call the dumb units? English system. It's pounds over area. Now, for reasons that make no sense at all, because the English system makes no sense, this should be pounds per foot squared. Okay? However, because these people are clowns, okay, they prefer the pound per inch squared, which is a PSI. Okay, and this is a PSF. Okay, now I recommend in all of your problems, there's going to be so many problems where they give it to you in PSI, and I highly recommend you convert to PSF. Okay, and for those of you who struggle with that, let's remember that pound per, let's say, suppose you got pounds per foot squared. Well, now you're going to say, okay, well, 1 foot squared equals 144 inches squared, and so that's how you would convert. So let's suppose they gave it to you as like 20, then it would be 20 over 144 PSI, right, if you were to go that way. If you go to the other way, like let's suppose you were given 72 PSI, well, now you've got pounds per inches squared. So you'd say, well, 144 inches squared and 1 foot squared, okay, and then you would get 72 times 144 PSF if you had to convert. Okay, so that's how you would do that. All right, so anyway, so that's the idea. And then the last bit we kind of want to get at, okay, and I was kind of talking about this sort of, is what about direction, right? What is the direction of pressure in a fluid, of pressure in a fluid? Okay, so right now, and this is going to happen from time to time in our in your fluids education, in your engineering education, whatever. And what I'm going to do is I'm going to do a derivation that's going to kind of prove a point here. Okay. Usually, and this obviously depends on your course, but what I recommend with derivations is that you follow along, and at least in my course, I'll always tell you if you need to know the derivation. In this case, you don't need to know the derivation. However, if you just follow along, you kind of see what's going on. You can copy into your notebook if you want, whatever. But the idea is I'm making a point here with this derivation. So, but just watch and kind of soak in as much as you can. And the more of these you see, the more they start to make sense. If you wanted to copy down in your notebook so that if you came in and you wanted to do a similar derivation for something else, then you could alter it and get relationships that were more meaningful for you. Okay, so let's start. All right, so I've got a wedge of fluid. We're going to consider this wedge. So this is fluid in here, okay? And it is underneath a whole bunch of other fluid. So this is just inside, your swimming pool or something. And it's got some dimensions. It's got delta X, it's got delta Y, and then on the diagonal, it's got delta S, okay? And so what I want to do with this fluid is I want to think about the forces on it. Okay, so this is a free body diagram, okay? It's not a complete free body diagram because what I'm doing is, okay, so these are the edges of my fluid. Let's outline them in like green. And so whenever you do a free body diagram, you want to think about the forces on your system, okay? In this case, it is this wedge. And so we have two types of forces. We have body forces, which is, well, in this class, there's only one body force, which I haven't drawn yet, which is weight. Weight is always a force, right? So this is a force that a body force is one that acts on your object without touching it. Okay, so it's weight, or maybe it's magnetism or something like that. So there's your weight. Okay, so now in the meantime, the other forces are surface forces, and so surface forces are basically forces that are touching the surfaces of your system. So the surface of my system is in green. And the only thing, so basically, like, I took my system and I just took it out of that whole world. And so when I did that, I now have to replace the rest of the world with the forces that, like, wherever it was touching the rest of the world, there was a force. There was some sort of effect from the rest of the world. And in this case, that effect are these pressures. So I've got this PS, as I'm calling it. Okay, so that's the pressure on, I guess, the slanted line. S usually means streamline, but in this case it'll mean just kind of like the slanted or the sloped line. We've got Py, which is the pressure in the y direction. Okay, and then we've got a px right here. Okay, and so those three pressures represent the effect of the fluid outside on this this wedge. Okay, I should note that this is a 2D. We are not going to deal with the we're not going to deal with the third dimension. The into or out of the board. We don't. I don't want to deal with that. All right, so we're going to assume that this is hydrostatic. Okay, so if it is hydrostatic, okay, you guys have had statics. So if it is hydrostatic, then you know as well as I do that means the sum of the forces in the x direction must equal 0. So let's zoom in a little bit so we can get a little bit bigger. Okay, so you know this. So knowing this is pretty useful. Okay, so that means, well, first of all, that means I'm in the x direction. It means I don't have to worry about this weight or the py because these things are acting in the vertical. So instead, I've got pressure in the x direction, and it is acting on this face. Okay, so like as we work on these faces, let's do them one at a time. So here's red. It's acting on that red face. So so it is that pressure times that area gives me that force on that thing. So I'll say delta y, and then whatever this imaginary dimension is into and out of the board, delta z. Okay, so you see that this is the area of that face, and this is the pressure on that face. So you take the pressure and you multiply times the area on that face, we get a force. So that is the force on that. It's in the positive x direction, so we'll give it a positive sign. Okay. Now we want to deal with the pressure or the force from, the horizontal force from this PS force. So we're going to be on this face right here. Okay, so if we were to look at that face, it's a rectangle with units with delta S by the into or out of the board. Okay, and this one's going to have a negative sign because it's working in the negative x direction. So that's going to be PS, P sub S, and then we're going to do the sine of that angle because it is not acting straight up and down. We're only getting the, we're basically getting, let's see, where can I draw this triangle? Okay, so if it's looking like this, right? Okay, if that's the direction the pressure is going in, then we want to know how much of it is going. We want to know this side right here. And if this is theta right here, okay, this is also theta. So this is the opposite. This is the hypotenuse. Okay, so if we take PS, that's the hypotenuse, times the sine of theta, we'll get the opposite. Okay, and if you can't see that, I highly recommend doing a little SOHCAHTOA on your own, and you'll see that that's the way it works. Okay, and then so this is the pressure, or the direct, the pressure in the x direction, and then we are going to do delta S over times delta Z. So that's the area equals 0. Okay, pretty cool. Okay, so now we need to think a little bit about some trig, and I'm going to kind of do a little trig aside over here, aside, which will help us with this derivation. And what I'm going to do is I want to think about this triangle like this. Okay, and this angle right here, theta. Okay, and we've got sides delta y, delta x, and delta s. And based on this, the sine of theta equals the opposite, delta y, over the hypotenuse, delta s. Okay, and just because I know that I'm going to need it coming up, I'm going to do the cosine of theta equals delta x over delta s. S, not z. Okay, so that will come in handy. Okay. Okay, so this is an aside. You'll note that in lots of my work I do asides. It just kind of helps me organize. Anyway, so what we're going to do now is I'm going to plug this in right here. Okay, and I'm going to end up getting px. Well, let's kind of zoom in a little bit. Okay, because now we're doing just some algebra, so we don't even need the shape for the moment. Okay, delta x, or delta y, delta z, minus ps. The sine of theta is delta y over delta s. Oh, that's nice. It looks like stuff's going to cancel out. Delta s, delta z equals 0. Okay, you can see these delta s's cancel. And let's see, delta y is everywhere, is on all the terms, so I can divide that from both sides. Delta z will cancel. Okay, so now I get px minus ps equals 0. So px equals ps. Well, that's cool. So basically, for any hydrostatic fluid, okay, for any hydrostatic fluid, the pressure on this angled side, this angled side right here, equals the pressure on this vertical face. Okay, so that's cool. Okay, now remember, this is for a hydrostatic. Okay, so let's zoom in and let's see what happens if I do. Okay, so obviously, if we've done this case, then we're going to want to do the sum of the forces in the y direction equals 0. Okay, and we're going to use similar logic. Of course, we have to deal with this weight, which is annoying. But there's only two pressure terms, just like in the x direction, but there's only two pressure terms. Okay, so we'll do, let's see, let's do py. Yeah, okay, py. And again, so let's see if we can get a different color here. Let's get yellow. So we're on this face right here. Okay, so py times the area of that face. Well, the area of that face is delta x times whatever the dimension is into and out of the board, which is going to be delta x. So it'll be, excuse me, delta z. So delta x, delta z, okay, minus, because this pressure term, the ps term, is now acting downwards, so it gets a negative sign. And this is going to be the cosine of that angle. Okay, because if I go look up here, if I zoom in on this little guy, okay, this time I'm looking for the adjacent. Okay, there's the one that's going downwards. Okay, and again, do a little SOHCAHTOA if you need to make that make sense to you. And we need the area of that face. Okay, so that's this face right here. Okay, so that face has an area, a length of delta s and a width of that delta z, so that into or out of the board. Okay, so that's going to be delta x, delta z. Excuse me, that's not delta x, that's delta s. Okay, you know, keeping track of these little guys, you know, or girls, keeping track of them can be problematic. All right, now the last force we need to deal with is this weight. And weight is different in fluid. So normally you would do equals mass times gravity, right? That's how you do this in other courses. However, in fluids, you know, I don't know what the mass of that object is. So usually what we do is, in order to get mass, it has to do with the volume of fluid we have. So usually what we do is we say, well, it's going to be rho, so that's the density. That's mass time, the density is mass divided by volume. And if we multiply mass by volume, we get mass times gravity. Okay, so what I've done here is I've replaced mass with rho v. Okay, so now we're dealing with the volume of fluid. Okay, the mass per volume times volume gives you mass. Now the cool thing about writing weight this way is that I can then rearrange this to make this rho gv. Okay, like no big deal, like whatever, I just changed the order. But rho g, this is the specific weight of the fluid. So this is gamma times volume. Okay, and we're going to use this a million times in this course. So always remember weight equals specific weight times volume. So that's weight per volume times volume, okay, which I think makes sense. Okay, so what we're going to do here is then, but in this case, the volume is a half triangle like prism. Okay, so what it is going to be the area, this area, okay, times the width. Okay, so the weight equals gamma. Now I need the volume. So the area of that triangle is 1/2 of delta x times delta y. Okay, so that's the area of the triangle. And then we're going to multiply times the length of that prism, which in this case is delta z. Okay, so that's my weight for this problem. Okay, so I'm going to go over here, and I'm going to subtract the weight, which is gamma times 1/2 delta x, delta y, delta z. Okay, all of those forces add up to 0 for a hydrostatic fluid. Okay, so let's zoom in because now we're kind of in a mathy math world. Okay, the first thing we notice, just because it's going to make our lives easier, these delta z's are going to go away because every term has one, so I can divide the whole thing by delta z. Okay, I could almost do that with delta x, but I can't, right? So the problem right here is I've got this cosine of theta. So what I'm going to do is I'm going to plug in for that using this relation we got earlier. So I'm going to get delta x over delta s. Okay, delta s, and this is going to be ps. Okay, I'm going to fill in the rest of this. Okay, and every time I do this derivation, I get a little bit scared at this point. Anyway, these delta s's cancel. We got one on top and one on the bottom. The delta x's, you have a delta x on every term, so if you divide both sides by delta x, these go away. Okay, and I'm left with, kind of an interesting expression. I get py minus ps equals gamma on 2 times delta y. Okay, yeesh, yeesh. Okay, this is not as pretty as the other one. Okay, but so two things that are kind of interesting here. One is theta dropped out. Okay, so direction doesn't matter. Doesn't matter. Okay, and so that's important. The other thing is I can take a limit of this. So I can say, well, as delta y goes to 0, so as this gets smaller and smaller and smaller, okay, py minus ps goes to 0, okay, because this whole side will disappear. Okay, so basically, so this is important, okay. So that means that at a, oh, where did my little record go? Come here, buddy. Okay, that means that at a point, okay, so that's a very small size. So at a point, px equals py equals ps. Okay, so put in plain language, okay, so we're going to zoom out here, so I can put this in as plain a language as I can. Pressure is the same at a point in all directions in a static fluid, okay? And that was the point of this derivation, is to show you this, okay? And this is really, really important. And in some ways, or in every way imaginable, in some ways, I don't know. This is logical to me because if the pressure were not the same in all directions in a static fluid, then the fluid would flow in order to accommodate that pressure, okay? Now you might say, well, what about when I'm in a pool and, the pressure is clearly, if I swim to the bottom of the pool, the pressure is higher at the bottom of the pool than it is at the top of the pool. So therefore, shouldn't there be flow from the bottom of the pool to the top of the pool? Well, there is difference in pressures between the top and the bottom of the pool, but that's not at a point. Okay, and we're going to talk about that in a second. But, right, in fact, before the day is up. But just for now, okay, just the key here is at a point, the pressures are the same in all directions in a static fluid, okay? So we'll talk about that shortly. But if there's a pressure gradient, then you won't have a static fluid. It'll flow. We have pressure gradient at the point, okay? So let's move on. Okay, so let's talk about expressing pressure. Okay, and we're going to do this, and this is, I think, actually, I always hate to say easy things in this class, but I think this is one of the easier things, but it does confuse students, and the reason it confuses students is because I don't spend a lot of time on it, and then you're just kind of expected to know it. So just, give this a little bit more time than I'm giving this in the course, and make sure to write this down somewhere on a cheat sheet or something so that you're always kind of aware of this. Okay, and there's basically three different ways to, well, there's really two different ways to do pressure. So the first one is absolute, and the other one is gauge, okay? Or this could be spelled gauge, Okay, also said gauge, but it's like, this is what Wiki says you spell it. I'm gonna misspell this from time to time as gauge like this. Okay, so just ignore me when I do that. Okay, I cannot get this word. It's the hardest word in the language. Except tomorrow. Tomorrow used to get me, but I learned it. Anyway, okay, so this, the absolute pressure, this is the actual pressure. Okay, cool. Okay, referenced to 0. Okay, we never use the absolute pressure. Okay, some of you may go into higher science or whatever, and you might actually use the actual pressure, but we never use it. Okay, so I'm going to say that I'm going to put in quotes never, because I don't want to tie myself completely to never using it, but it's very rare in society and the world for us to use the absolute pressure. And I'm going to make an analogy in a second that hopefully will make sense to you. Okay, and the gauge pressure is pressure referenced to atmospheric pressure, to, I guess, what they'll call local atmospheric. That used to be a hard word for me too. Pressure. Okay, at a gauge, and that's why they call it. Gauge pressure. All right, so here's my analogy. Okay, if I were to ask you what the temperature is outside right now, depending on where you grew up, some of you would say, oh, it's 75 degrees Fahrenheit. Some of you would say it's what's 75? I don't know. It's like roughly 18 degrees C. So a lot of you would say it's something like that. Okay, these are not necessarily equal. Okay, whatever. Anyway, so depending on where you grew up, you would say it was something like those particular things. I bet that none of you would give this to me in Kelvin or Rankine. Okay, right. So you'd have to add 273.15 to this to get the Kelvin, and you'd have to add 5 whatever to get the Rankine here. Right? None of y'all would do that, right? Because we just don't work with that system. So if we had something that was like really cold, we would just end up having so if something were really cold, maybe we'll use the blue for that, but if something were really cold, we might say, oh, well, it's like negative 2 degrees F outside, meaning it's, really cold. Okay, the similar, for this might be, let's see, what would that be? I can't really do that math. I don't know, that'd be like negative 15 degrees C, right? So notice in our standard day-to-day practice, okay, we can get negative numbers. Okay? It doesn't mean that there's negative thermal energy in the air on this day, right? It just means that it's below wherever our random 0 point is. So if you use Celsius, the 0 point is the freezing temperature of water. If you use Fahrenheit, the freezing temperature is, I don't know where they came up with that, some random point, okay? But if you use Rankine or you use Kelvin, these are like the absolute temperatures, okay? The absolute temps, okay? And they cannot be negative. Okay. Similarly, with pressure, we have something called an absolute pressure, and that tells you what the actual pressure is, and it cannot go negative. Okay, so I would say cannot go negative. Okay, we never use this though. Okay, instead we use the gauge pressure, which can go negative. Okay, so when it comes to fluids, pressure can only push. Okay, but sometimes we'll give it a negative value, which would make it look like it could pull, but it cannot pull. Okay, it just means that, so negative values, negative means below atmospheric. Okay, in much the same way that for temperature, a negative value just means below whatever the random whatever the random 0 point is. So if you're in Celsius, if you have a negative temperature, that just means you're 15 degrees below the freezing point of water. Okay, so yeah, so hopefully that helps you kind of understand what the difference is between these two. Okay, so for example, if I were to talk about a vacuum for these things, so the vacuum, if we were in a vacuum, okay, that means somehow we managed to get rid of all of the molecules in a container or something, then the absolute pressure would be 0. Okay, and the gauge pressure would be, depending on the system we were using, it might be -1 atmosphere. Okay, with 1 atmosphere being, what we typically say is the absolute pressure of the atmosphere. Okay, now there is a way that we deal with this, and let's talk about this real quick. So I want to zoom in here, and I want to talk about atmospheric pressure. Okay, atmospheric. Okay, and I'm going to give you a whole bunch of different ways that we deal with this. And of course, all of this is not set in stone, but this is what you'll do for these engineering problems if you don't know anything. So usually it's 1 atmosphere. That's one way to say the atmospheric pressure. Now, obviously, it can actually fluctuate above and below that. But typically, that's one of the ways we'll denote it. It could be 14.7 psi-A. Okay, so that's pounds per square inch. This A means absolute. So if you see that A, it means absolute. Okay. It could also be 0 psi-G. Okay, so that means 0 psi gauge. Okay, and if you don't see a letter here, if you don't see a G or an A, you're always going to assume that it's gauge. Okay, it could also be 2117 psfa. Okay, 2117 pounds per square foot absolute. Okay, it can basically equals 0 gauge of any gauge. Okay, it's 101.325 kPa. Okay, now without even saying anything, you should know that this is absolute. Okay, because it's going to have to be 0 gauge for anything. Okay, fundamentally. Okay, I've now said that twice, really. And these are the more interesting ones, and we'll kind of get into these shortly. But it's 33.91 feet of water. Okay, now that's weird because all of these are force per area, and then all of a sudden we've got just something that's in feet of water, which is pretty weird. Or we might see 760 millimeters of mercury. Hachi-machi, that's weird, right? And then, or we could say 1013.25 millibars, and that's a weird one. We'll never use millibars in this course. Okay, so don't worry about this one. Okay, but we will use things like feet of water and millimeters of mercury, but don't get bent out of shape about that yet, because we're gonna work on that. But we'll talk about kind of what those mean. Maybe a little bit today and more in next class. Okay, so one thing to remember is, so we're still kind of on gauge to absolute, is I want you to remember, so for example, if I've got -10 psi-G, okay, what does that mean? Well, that means I'm 10 psi below atmospheric pressure, which we'll typically write as, let me change the way that I'm writing this. Typically, we'll write that as below the pressure in the atmosphere. Okay, PATM. Okay, so that's kind of what it means if you say something. Now, if I said I had, let's suppose I changed this and I said, well, what if I've got positive 10 psi-G? Well, that means I'm 10 psi above, okay, PATM. Okay, or mathematically, what we say is P absolute equals PATM plus the pressure gauge. Okay, and that's how you go from one to the other. Okay, if And we'll explain why we were able to use the gauge. That's going to come up here and there, but we'll talk about it as we go. All right, so now I'm going to zoom down here, and we're going to talk about, let's just go down here. Okay, we got some space down here. We're going to talk about Pascal's law. Okay, Pascal's law says that pressure is transmitted through a static, incompressible fluid to every other point in a closed system. I think that typically when people talk about this, they'll say not only is it transmitted, but it's transmitted without loss. I have a hard time imagining that it's actually without loss. I think basically that's like in the perfect system, the perfect incompressible fluid and whatnot, which of course doesn't exist. But you could just say with very little losses, I think we would be totally okay. Also a note for those of you who are interested is that you could easily say that that this is transmitted, the speed at which the pressure is transmitted through the fluid is basically the speed of sound. Okay, so you could imagine it's almost like a shock wave, although it doesn't have to be all that powerful, but something, it's a little pressure wave that's moving through your fluid, and of course sound is a pressure wave, so it makes sense that this would travel at the speed of sound. So typically the way that we express this is a hydraulic press, or typically the way we make use of this is a hydraulic press. Okay, so this is kind of a standard schematic of a hydraulic press, and what we're doing here is, so what we're going to imagine is that I've got some kind of fluid in here, in this, container, and it's got two pistons. Okay, I'm not really that great at drawing pistons, but they've got forces, forces acting on these pistons, okay? And the fluid is free to move, from left to right or through this tube, okay, depending on what happens. And right now, for whatever reason, this whole thing is static, okay? So neither piston is moving up or down, okay? So for whatever reason. And they're kind of on the same level. And it's like, okay, well, this is cool. What's going on here? Well, here's the cool thing about this, right? If this whole thing is static, that means that the fluid is not moving from the left to the right or from the right to the left. And so what that means, basically, is that the pressure here, like on the bottom side of this piston, and the pressure on this side of this piston are the same. Okay, because if they were not the same, then the fluid would flow from one to the other. Okay, if the pressure at here and the pressure here were different, then the fluid would respond to that difference in pressure and it would flow. Okay, but it's not flowing. Okay, so that means that P1 equals P2. Okay, if that is the case, that means that force 1 over area 1, okay, so that's the pressure being applied at that point, is equal to the pressure being applied at this point, force 2 and area 2. Okay, which means, okay, if area 1 is smaller than area 2, which, based on how I've drawn it, that appears to be the case, okay, then F1 is less than F2. Okay? You're like, okay, well, so what? So what that means, and, I remember teaching this, in the past, or at least the way that I put this for some people, when I taught high school or whatever, is I liked the idea of the mouse and the elephant, which was kind of like, well, it means that I could put an elephant, if I could draw an elephant right here. Okay, here's my elephant. I love elephants, and I'm doing this elephant a vast disservice. And I could put a mouse over here. Okay, and depending on the ratio of these areas, okay, I might be able to lift that elephant by just with the weight of a mouse. Okay, you might say, oh, well, that's cool, So like I could just, basically I can, it's a force multiplier, because of the hugeness of this area over here. If I make this big enough, okay, the pressure isn't very high, so I could I could just do this with my arm. Like I might be able to just, put a lever over here and crank the lever down and lift this elephant. You're like, well, that's cool. That seems like a impossibility, and it is not an impossibility. But this is almost like, one of those machines, and there's basically a huge mechanical advantage here. And you might say, well, why don't we do this for everything? And because there's the trade-off, right? It's all about work. And so what you also want to remember is that area ratio also says something about the ratio of the kind of how much height you get out of it. So if I go down, let's suppose I go down, I don't know, 10 units of length here. Okay, well, that's only going to push this thing up not very much, because this volume that this thing goes down will equal the volume that this one goes up. Well, I drew it on the bottom, so I guess it should be on the top, but it only equals the volume on the top that this thing moves up. So the bigger this area difference, the more you multiply your force, but also like the farther you got to go in order to get something to move. Okay, so I mean the comparable thing would be like your car jack or something like that, which also is a machine with a mechanical advantage, or lots of other things. So this is a hydraulic press, and or this is how we draw a hydraulic press. They don't usually actually look like this, but if any of you guys work with cars or anything like that, a lot of times we use these to lift cars in a shop or something like that, because we need a huge mechanical advantage. And we don't really care how long it takes us to get there. We can just keep on going. And that's the same way it is with your car jack or something along those lines. Anyway, so that's the idea of the Pascal's law and pressure being transmitted through a fluid. This is not terribly important to this course, but it is an important fluids concept. So it's good that we talk about it. All right, so let's zoom. Look, these notes are so organized. Okay, so let's go down here, and let's do something else. Let's do some hydrostatics. Okay. All right, so here we go. So we've got a free body diagram. Well, it's not really a free body diagram right now. Right now it's just a diagram, but we're going to make it a free body diagram. And so what I want to start with, as I talk about this free body this diagram, which we're going to turn into a free body diagram, is we're going to derive this law. And I want to think about the forces on this particular, I guess it's a sliver of fluid that is kind of off at a weird little angle, okay? And the angle is in this S direction, so you can see I kind of wrote a delta S again. Usually it's a streamline direction. We'll do a few of these derivations. And again, this is a fluid, so there's this is all fluid in here. And what I need to do before I go any farther is I want to make this a free body diagram. So I want to think about the forces on this particular fluid parcel, okay? And so I'm going to say that, and I'm really only going to concern myself with, so you see I've got directions X and Z, and I want to think about things that are moving in the S direction. So S is just some random direction, okay, an angle theta from the X direction. Okay, and so on the back of this thing, pushing it along, is some pressure multiplied times some area. So that's a force, pressure times area. Now on the front of it, okay, and that area is referencing this frontal area here. And then on the, there's some pressure resisting that flow on the front of this thing. Now that pressure is different from the other pressure. Okay, so it's P plus delta P. Now the delta P could be negative, it could be positive, I don't know what it is, but basically the pressure in the front of this tube could be more or less, I don't know, okay? But I take that pressure and I multiply it times the area on the front, okay? Again, by the way, this is derivation. Watch it, pay attention, learn the result, okay? If you can't quite grasp all the details, that's okay. Okay, so again, that area is this frontal area. Okay, now do we have any other forces on this? So let's see, we've got body forces. So the body forces is, at least in this course, is always the weight or the gravity. Okay, so I'm going to draw this as a long one to just kind of get it out of the way. Okay, so there's my weight. Okay, and then I've got a force, I've got this PA, and then I've got P plus delta P. What about on these faces? Do I have any forces on those? Yes, I do. Yes, I do. Says the person in the back, okay? Because those were touching the rest of the world. So if you're touching the rest of the world and I sliced it, there's going to be a reaction. There's a force that was there that we're ignoring. So on a free body diagram, we need to include those. I'm going to make those in this obnoxious red color because I don't feel like dealing with those. Okay, so there'll be a pressure here and a pressure there. But we're not going to deal with those in this case just because that's not the That's not the problem that we're doing right now, okay? So I just want to deal with in this random direction, whatever this S direction forces, okay? So let's deal with these forces as best we can. And actually, before we move too far, I'm going to look at this triangle right over here. I guess I'll do it in yellow. Okay, so here's a triangle right here. Okay, because I'm doing this because I know what I'm going to need. But let's just note that the sine of theta is equal to the opposite, delta z, over the hypotenuse, which is delta s. Okay, and I'm doing this because I know that I'm going to need that. Okay, it just kind of helps. At least it helps me anyway. So that's an aside. Okay, so we will use that shortly. All right, so let's start doing, so now this, we should note this derivation. This is a static fluid. Okay, so if it's a static fluid, that means, well, that means it's not moving. So if it's not moving, then the acceleration is 0, which means the sum of forces in any direction, in this case the s direction, equals 0. Okay, it's always nice when you're statics and like you learned that so well and you're like, boom, I can use that whenever I want. You know, like I already know this stuff. All right, so in the positive s direction, so this is the s direction going this way. Okay, in the positive s direction, we've got p times a. Okay, in the negative s direction, we've got minus p plus delta p times a. Those are nice because those two forces almost have the same form. And then we have to deal with this weight. Okay, and just like last time, okay, so let's consider this weight. Weight equals gamma times volume, okay, specific weight times volume, equals the specific weight, and in this case the volume is, well, let's see, so it's not a triangle like last time, it's a rectangle with delta S times this area, okay? So it's prismatic, okay? So we've got that force, which is gamma times delta S A, okay? And now we have to deal with the fact that the weight is not acting in the S direction. So we have to do our trig. So let's kind of look at it here. Well, let's see, how can I do this? Maybe if we use, what color? We've kind of used all the colors at this point. Red is gonna pop. So let's do some red right through here and back this way, okay? So we want this S direction right here. Okay, so that's gonna be W times, well, let's see, what angle? If this is theta, then this is also theta. So W times the sine of theta. Okay. So basically we're gonna take our weight, and now we need to so this is the weight, W, and we need to multiply it by the sine of theta. Sine of theta. Okay. Okay, so before we go to, at this point we're kind of in an algebra situation. We can almost ignore the diagram for a brief moment. So let's zoom in on our math. Okay, and let's see what we can do here. Well, I don't want to completely get rid of what that sine of theta equals, but you probably have it written down somewhere. Okay, I hope so. So let's see what we can get rid of. Okay, first of all, this area is going to pop through everywhere, right? All the terms have an area on it, so we can get rid of all of those. I want to get rid of that sine of theta, so I'm going to do that in the terminology that I did up here, which was delta z over delta s. So this becomes delta z over delta s. Okay. And I think we're about ready to simplify. So I get p minus delta p, okay, minus gamma delta s equals 0. Okay. And you should be able to see these delta s's will cancel out. Okay. And p minus p cancels out. Goodbye p minus p. Okay. Okay, so now we can bring delta p, or we can bring one of these to the other sides. Let's say delta p equals negative gamma delta z. Okay, ooh, this is looking really exciting. I love this. So now I'm going to divide both sides by delta z. I get this wonderful thing that looks like this, delta P over delta Z equals negative gamma. And if I wanted to like really make this like a really wonderful thing, is if I said, what is the limit as all these sizes go to 0? So let's make it, in this case, let's make it delta Z goes to 0 of this whole expression. And I get dP dZ equals negative gamma. Okay, now this is super powerful. This is the hydrostatic law. Okay, and this is super important. Okay, now there's a few different ways that this gets written. So this is one way. I'm going to box a bunch of them. So you got to know all the different ways it's been boxed. So a few of the different ways you can do this. So we can go up here, and I can separate variables and get dP, son of a monkey's uncle. Sorry if anybody in this class is a monkey, and your uncle is offended. I do apologize. One of my old roommates used to always say, son of a monkey's uncle. I always liked it. I have no idea what it means. All right, so I can separate variables, and it looks like this, negative gamma dz, like that, and then I can integrate both sides, and I'll get delta P equals negative gamma delta Z, okay, from which I can say delta P plus gamma delta Z equals 0. Okay, it's like, oh, what's going on here? And so the way that we typically write, the way that we think about this is we say, or P plus, yeah, this should be a gamma. I can hear myself saying gamma as I write something else. Gamma Z equals a constant. Or if I divide both sides by gamma, I'll get P over gamma plus Z equals a constant. Now a different constant because I've divided by gamma, right? So this case, okay. Now I want to make a note here. The difference between these two sides here is that over here gamma can change, and over here gamma is constant. Okay, so anyway, so typically, and then the last way that we do this is I'll pick 2 points in my fluid, in a hydrostatic fluid, and I'll say pressure at point 1 over gamma plus the elevation at point 1 equals pressure at point 2 over gamma plus the elevation at point 2. Okay, and this is probably the most useful form of this equation. Okay, this is the most useful. Okay, so I'm going to kind of like show you how we work with this. You definitely, I don't know how I can, this one is the easiest version of this equation. And this equation is going to get so much more complicated because right now this is the equation that works for hydrostatics. I'm going to make this work for every situation in the universe, okay? But we're just going to keep on adding things to it. And at first, like this one looks complicated, but by the end of the semester, you're going to be like, I wish we could go back to that one, okay? And you'll ultimately end up memorizing this for the rest of your life without me asking you to memorize it. So I did ask you to memorize the fluid properties because while a lot of those will get memorized just by using it, it helps to kind of knock it in. This one is going to be memorized just by using it, okay? So let's kind of start, and we're going to talk about the hydrostatic law, and I'll kind of talk about how it works. All right, so I've drawn a tank, and the tank is, I don't know, so here's my XZ coordinate plane, so Z is vertical. And I've got, let's see, I've got 2 points in my fluid. One is at the fluid surface, and the other one is some depth Z, or excuse me, H, below that point, okay? So I guess I could zoom in a little bit, not make it so freaking tiny. Anyway, so we got these 2 points, and what I want to do is I kind of want to I want to kind of get at what is the pressure at point 2. So this is a static fluid, okay? Static fluid in here. It's not moving. So I can get at what the pressure at 2 is by just kind of I don't know, by using my little law here that I just came up with. Okay, so my little law, it's not mine, it's yours now. P1 over, I have given it to you. Okay, feel happy. Okay, P2 over gamma plus Z2. You're like, okay, I don't like this law. There's stuff here. All right, so we're going to look at these 2 points. And so, well, here's the pressure. Here's point 1, and I don't know what the pressure is right there. So I'm just going to call it P1 over gamma. Okay, that's fine. And then what's Z1? Well, Z1 is defined as Z1. Okay, this is not helping me very much. Okay, the pressure at 2 is, I don't know, but it seems like it'd be higher than at P1. P2 over gamma, I don't know what that is. And then Z2, well, I don't know what Z2 is either. Dr. Wagner, are you wasting our time? Yes, I'm wasting your time, right? None of that was very helpful, okay? So we're going to have to kind of start getting at this. So let's rearrange this sucker. And I'm going to say P1, I'm going to bring the P2 over to this side, over gamma. I'm going to do it like this, equals Z2 minus Z1. Okay, that's interesting, because I know what Z2 minus Z1 is, right? Because I've got Z2 minus Z1 is a negative H. Oh, that's interesting. Okay. And P1 minus P2, well, here's something, and I haven't told you this yet, but P1 is the atmospheric pressure. Okay, what's atmospheric pressure? Well, let's just write it as PATM for a moment, and then we'll kind of get at this. Okay, PATM minus P2 over gamma. Okay, now this is where we have a choice. Okay, and this is an important choice. Okay, PATM. Well, it could be a lot of things. It could be zero gauge. Okay, it could be, well, if I'm choosing coordinate systems, I'm going to choose. If I'm choosing unit systems, I'm going to use 101.325 kPa if I'm going absolute, because that is the easiest one. Okay, so remember, this is absolute, this is gauge. Now I ask you, which one of these is easier? Well, this is easier. Okay, both of these are PATM, but this one's easier. Now the key here is, as soon as I choose zero gauge, that means as soon as I choose to use the pressure in terms of gauge, that means my entire problem is in terms of gauge. So if I do that, then what I'm solving for here for P2 is a gauge pressure. Okay, so you want to write that down. As soon as you choose a pressure, if you choose a gauge pressure, then all the other pressures in your problem have to be gauge. Okay, which of course is what I'm going to recommend you always do, but that's entirely up to you. Okay, so if we zoom in here, and I'm going to do that, I'm going to make 0 my pressure. Okay, for gauge minus P2. So P2, whatever we solve from whatever we get from this, is going to be a gauge pressure. Okay, over gamma equals negative H. Okay, and if we solve that, oh, look at that. P2 equals gamma H. Okay, sweet. Okay, so we love this, by the way. And here, P2 is gauge. P2 is gauge. Okay? Now, what this means, and if I want to step back just a second to what we had a step before, is I had P2 over gamma equals H. Okay, so what I have here is I have pressure expressed as height. Okay? So in this way, so you can see it's expressed as a height, and this gamma, okay, the gamma is the specific weight of the fluid. So this is a height of a particular fluid, as a height of a particular fluid, okay? And so if I go back, way back, I don't know where it is, somewhere along here, I talked about ways to express atmospheric pressure. Okay, I don't know where I put it. But anyway, one of the things that we talked about when we did that, or I talked about, and you had to listen to, was that you could express it as a certain number of, here we go, millimeters mercury. Can I zoom in, you punk? All right, there you go. Okay, is And so these two red boxes, 33.1 feet of water, 33.91 feet of water, or 760 milligrams of mercury. So we're basically trying to think of things, and these are things that aren't naturally expressed as feet or units of length, but we're expressing them as units of length because of this hydrostatic law. Okay, so 760 milligrams of mercury is basically how far this pressure could drive upwards mercury, 760 millimeters. How far could it drive upwards water? 33.91 feet of water. Okay. Anyway, so that's the idea. So this is the hydrostatic law, and you're going to get more and more comfortable with this because you're going to use it an awful lot. Okay. So we're at an hour right now, so I've got 15 more minutes, and we will not use all of that time. So you can rejoice. Okay. So I'm going to go over here, and I'm going to do more stuff with this hydrostatic law. Okay. So this is just going to be an example. Okay, and I want to consider a few things that are a little bit difficult here. And so let's start with, here's an example of immiscible fluids. So immiscible fluids are fluids that cannot mix with each other. Okay, so oil and vinegar. Okay, we've got two free surfaces here. I've got fluid B and I've got fluid A. Okay, so I'm going to give you this. Okay, gamma of A is greater than gamma of B. Okay, so the A is more dense than B, or A, really what I'm saying here is that it has the specific weight is greater than the specific weight of B. Okay, so the question is I want to know what is the shape of the pressure distribution. Okay, that's the question. Okay, now at this point, for a lot of you, you're going, I don't even know what you're talking about. and that's totally reasonable. Okay, so here's X coordinate, here's Z coordinate. All right, so what is he talking about? The pressure distribution. And so what I'm going to do actually with this one is, let's get a different color. I'm going to draw Z right here. I'm going to draw X right here. And I'm going to try to delete this other one because it's kind of in my way. All right, so, okay, I thought I deleted it. All right, anyway, so now we're looking at it. We're like, all right, well, let's go up to the surface right here. Okay, what's the pressure at the surface of this fluid? And remember, this is a plot. I'm not drawing anything that exists outside of it, but this is a plot. And so the pressure at the surface of this thing is pressure, would you please write, you jerk? Pressure atmosphere. Okay, so what's the pressure of the atmosphere? Well, you have a choice, right? We could make it absolute. I could make it 101.325 kilopascals, but I think it's going to be easier to make it 0. Okay, so let's make it 0. Okay, so that's a value of 0. So actually, I guess this won't be the x-axis. This will be the pressure axis. Okay, this will be pressure. Okay, so we've got a value of 0 right there. Okay, now, what is the pressure, I don't know, like right here? Well, we don't know, but I mean, if you think about your experience swimming in a pool or something, you know it's going to be greater than it is at the surface. It'll be positive. Okay, well, how about this? Okay, this was the hydrostatic law, dP dz equals negative gamma. Okay, so what that means is that as z, okay, so here's z, okay, so that means the change in pressure with depth is negative gamma. Okay, so the slope of P with respect to Z is negative gamma. So in this entire fluid, B has a constant gamma, so the slope of this line is going to be constant. Okay, so basically we're going to go like this. Okay, the slope of the line is constant, that's dP dz. Okay, and the slope of that line is gamma. And you might say, well, isn't it negative gamma? Why are these values increasing? Well, because Z is decreasing, because we're going down in the fluid. So because Z is decreasing, you take that dz, which is negative, and you multiply it by this negative gamma, well, we're going to get a positive, so we're going to get an increase in pressure. Okay, so typically the way we draw this, we actually draw arrows here to indicate that this is a push. Okay, technically this is on this side of the fluid, pushing outwards. But it's a plot, not a picture. Okay, so then And what happens as we move further into this problem? Okay, so now we hit we hit A. Okay, so we hit fluid A, and we note that fluid A is more dense than fluid B based on this. Okay, or its specific weight is greater. So the slope of this line is going to increase. So this is going to be harder for me to draw, but the slope is going to increase, okay, until it gets down to the bottom of the tank. Okay, so the slope of that line is gamma A. Okay, so the slope of this line, slope is gamma B, and the slope of this line is gamma A. Okay, and that's how we solve it. Okay, one thing I will note, okay, if I were to just draw a bunch of possibilities, okay, is let's suppose we had this. Okay, let's imagine this is a pressure distribution. Okay, is this possible? Okay, and the answer is no, this is not possible. And you're going to say, well, why? Why is that not possible? The reason this is not possible is because the slope of these lines tells you something about their specific weight. Okay, and notice that so this has the highest specific weight, okay, because it has the steepest slope, and it is sitting on top of this fluid. Okay, so it is not possible, because what would happen is if you put these fluids in this situation, the more dense fluid, which is this one, would sink to the bottom. Okay, it would respond to the fact that it is denser and it would move downwards. Okay, the only real possibility is you could have a situation like this. Okay, so that would be a single fluid. You could have fluids that get denser as they go down, like each separate fluid looks like kind of what we drew up here. Okay, in this case. Or you can end up in a case where, like in the ocean, where the density just keeps getting more and more extreme. Okay, and it keeps getting more and more extreme because the fluid gets saltier and colder. Okay, and both of those will make the fluid more dense. Okay, so as long as it does that, it cannot go the other way. Like it cannot do this. Okay, it cannot do that. Okay, because if it was doing that, okay, in which case we would draw all the arrows. Okay, if it did that, then this would be less dense, and this would be more dense. Okay, and again, remember, it's all about the slope of that line. Okay, so this cannot happen. Okay, so that's kind of the gist of it. I think we've kind of got everything. So one last little bit over here. Okay, so we want to think about, so these terms, if I go back and look at this most useful equation, the most important thing we learned today is this. And this is called head. So this is pressure head. And I'm going to talk about this a million times. This is elevation head. Okay, and this is a pressure expressed as a length. This is elevation expressed as in length, although that's pretty straightforward. But let's talk about this. Let's talk about head, quote, unquote, as pressure. Okay, so if you have, for water, okay, if you have 1 psi, 1 pound per square inches, okay, then I could say, well, what is that in terms of head? Okay, well, first of all, I want to convert 1 psi to PSF, so that's 144 PSF. Okay, and then I want to consider converting pressure to head. Okay, so let's suppose I've got 144 PSF. Okay, I'm going to divide that by the gamma of water, which is 62.4 pounds per cubic foot. Okay, you should learn that number. It's going to come up. It's going to come handy. And that equals H, which in this case equals 2.31 feet. okay? So 2.31 feet of water will have 1 psi at the bottom, at its base, okay, if we're working in gauge, okay? So that's pretty cool. What if we did the same thing with mercury? Okay, what if I wanted to do 1 psi of mercury? Okay, so we'll do P on gamma equals H. Okay, now in this case, this is going to be a little bit different because, so let's suppose I'm going to put gamma of water for that one. This is going to be the gamma of mercury, which is Hg. Okay, so what we're going to do here is I'm going to change this equation to P over, now rather than dealing with the specific weight of mercury, I'm going to deal with the specific gravity of mercury times the gamma of water. Okay, this is a substitution we're going to make 10,000 times in this class. Okay, so this will be the S of mercury equals H. Okay, so the same thing. Now I'm talking about 1 psi. So we've got 144 psf divided by the specific weight of mercury, 13.6, or sometimes 13.55, times the gamma of water, which is 62.4 pounds per cubic foot, equals H, okay? And in that case, it equals 0.170 feet, okay? So 0.17 feet of mercury, and this one's water, okay, we'll have 1 psi at the bottom. Okay, so you can kind of see that, you know, mercury is a lot more dense. Okay, it doesn't take nearly as much of it to generate those kinds of pressures. Okay, so what's the last thing that I want to make sure that you get? Okay, if I go back to this one real quick. Okay, this will be the last thing for the day, which I guess it has to be because we're running out of time. But what would happen if, let's suppose that I came in here and the surface were not atmospheric. Let's suppose like I capped it and I either filled this with a fluid or I pressurized, but whatever I did, I pressurized it, so that there's a pressure at 1. So let's suppose P1 equals, well, I don't know, 5 million. Let's just say 5,000 kPa. Okay, so it's got some pressure right there. Okay, so the nice thing about this is the relation we had over here, like when we solved this earlier, is I was able to say, well, P2 equals, this is going to be gauge. Okay, well, as I said, P2 equals gamma times H. Okay, but now what I've done is I said, well, P1 equals all this stuff. Okay, the pressure at 1. Well, what did that do? Okay, so that increases the pressure, okay, from Pascal's law, that increases the pressure in this entire fluid by 5,000 kPa, okay, if I pressurize it. So I take my earlier result, and I'm just going to add the pressure at the surface, okay, which in this case is that 5,000. So I would just add the 5,000 to the result I got earlier. In effect, we've already done this. We did this right here, okay, where I added PATM from earlier, just so happened that PATM was 0. Okay, so in a lot of ways, this is kind of easy, right? If you want to know the pressure in your fluid, you go to the surface of the fluid, and you say, what is the pressure there? Pressure here equals what? And then you say, well, I want to know what it is at P2. So this is P1. And you say, oh, well, P2 equals the pressure at 1 plus whatever the change in pressure is as I went from P1 to P2, okay, which is going to be gamma H, okay, and that's what we're going to be working with next class. So if that doesn't make a lot of sense to you, it's okay. That's going to be the whole class next class, okay, so that's next class. Okay, next week on Batman. All right, anyway, again, take care of yourselves. Know that even though I don't know you, normally I would tell you guys that I loved you guys, and that's a little weird. But you know, I do care for you, and I'm working to help you. Even though I don't know any of you guys, you're just names on a roll, which is really quite dumb. But that's the world we live in right now. So hopefully you're enjoying this rainy Monday. I'm gonna go take the dog for a walk, and hopefully, if you don't have a dog, you do have a place where you can go walking and kind of just let it all out. So this is the day. And these were the objectives, if we can zoom over there, and hopefully these make sense, okay? I think we did all these things. So take it easy, and next class we'll get into some really awesome stuff. So be easy and be wonderful, and that's all. Take it easy. Oh, I got 10 more seconds.